Cloud. Okay. All right. Hello, everyone. Today we're going to be discussing Symmedians. I know this is probably a kind of advanced topic, especially for AIME level, but for those ready for Olympiads, I think it's pretty cool to learn about these. It might help you with some problems, and besides that, they're just very elegant compared to AIME Bash.
Cool. Before we get officially started, can we get a would you please raise your hand, the reaction? If you have heard about Symmedians before, just heard about the word before tonight. Is there anyone? You can raise your hand in the on the lower bar near the rig. Oh, cool. Oh, there's plenty of you guys. How about if you actually know something about it, like some stuff? Great. Cool. So, how about let's get officially started? I hope you're gonna learn more about this by the end of today.
Okay. So before we get into Symmedians, we need to first define an isogonal Sevian, since that's a very important part about what a Symmedian actually is. So, how do we, okay, annotate, okay. So let's just first consider a triangle. Let's consider, let's just consider a triangle ABC like this, okay? And you know what a Sevian is, right? It's basically, we have a segment that comes from one of these points and goes to the opposite side. And let's just denote one of this, let's just make two Sevians, P that go to P and P prime. Now we call the Sevians AP and AP prime. We call them isogonal if and only if this angle is equal to this angle. Like, for example, just using some numbers, if this is 10 degrees and this one's also 10 degrees, we would call AD and AE isogonal. So that's just an example.
All right, guys, does this make sense? Because please ask questions. There's no dumb questions, and if this doesn't make sense, then nothing else today will make sense. So please ask if this doesn't make sense.
You can message either me or Steven in chat if you have any questions, or you can message everyone if you want to.
Okay, so to prove I actually know this, let's have a practice problem. Please prove that for triangle ABC, the circumcenter O and orthocenter H, AO and AH are in fact orthogonal. Is there anyone of you guys who do not know what is the circumcenter and orthocenter? Like I assume all of you guys know that. Great. All right, how about let's have a courageous volunteer to share their proof. First of all, do you guys understand what I'm trying to ask here? To show, like, what does it mean by showing AO and AH are orthogonal? BAH equals to CAO. Okay, why? How do you prove that?
Yeah, could anyone help us prove that angles BAH and CAO are the same? Because knowing this, that just means that these two are isogonal Sevians.
OAB is greater than 0. Kevin, could you please clarify on what you mean by that?
So we're trying to find BAH is like greater than or equal to CAR, I think.
BAH is what?
Wait, hold on.
Basically, what we're trying to show is that angles BAH and CAO are the same. Can anyone tell me the angle of BAH in terms of any other angles in this triangle? We know that this is a right angle, so we can use that to our advantage.
Okay, so Franklin, do you want to show the proof?
Yeah, okay.
Oh, Charlie actually got it. Charlie, do you want to speak up and open your mic, please?
What?
Okay, can you share your proof, please?
How do I annotate? There we go. Can I annotate?
Let me see if I can enable. Yeah, you can annotate.
Uh, so this angle is equal to 90 minus this angle, and this angle is equal half of this angle. And then this is isosceles, so you can deduce that these two angles are equal, basically.
No, I think Charlie, that's how you prove that AO equals to AH by showing that angle BAH equals to angle CAO. Therefore, AH and AO are orthogonal.
To make the proof a bit more rigorous, we can write angle BAH as equal to 90 minus angle B in this case, since we have a right triangle. And there's like this one Evan-Chan theorem, but there's a much easier way to do it. But anyways, with some angle chasing, you can find that angle AOC is equal to 2 times angle B. And since this is a isosceles triangle because it's a circumcenter, we'll be able to deduce that angle CAO is also equal to 90 minus angle B, which is what we want, and as Charlie mentioned, that proves that AH and AO are isogonal Symmedians.
Indeed, and by symmetry, BH and BO are also orthogonal. And the reason being that there's really no reason for them not to be orthogonal if AO and AH are orthogonal. Like, it is completely symmetrical. If you want to prove it more rigorously, you can also write almost the exact same proof, except by replacing A with B or B with, I don't know, C or A or whatever. And the proof is still gonna be completely valid.
All right, next we'll look into isogonal conjugates. And let's let's just say in this case, we're going to define 2 points. Let's just call them P and P prime. I don't know why this one's a star, but like we don't make all the drawings for this. Anyways, P and P prime are isogonal conjugates relative to triangle ABC if AP prime and AP are isogonal, BP prime and BP are isogonal, and CP prime and CP are isogonal. So in other words, we must have this angle is equal to this angle is equal to this angle, and this angle is equal to this angle. And only in this case will AP prime and will P prime and P be isogonal conjugates with respect to triangle ABC.
Alright guys, does this definition make sense? Please hands up if it makes sense. This makes sense? Have you hunt down everyone who does not have neither thumb wrist? Okay, good, great. Okay, let's move on. So then we are going to have another practice problem, and which is find with proof the orthogonal conjugate of the circumcenter of the circumcenter O for a certain triangle, let's say ABC. So now I just learned the definition. How about try to find the orthogonal conjugate of the circumcenter? Didn't we say it was the orthocenter? Okay, so first of all, Kevin asked, does P always have a conjugate? That's honestly a great question, and you can deepen the question into, does P always have a conjugate, and if so, does it have a unique conjugate? And we're gonna prove it later. Okay, so Winston said, didn't we say it was the orthocenter? So it is indeed the orthocenter, but how do you prove that O and H, with respect to a certain triangle ABC, are orthogonal conjugates? Eden, can you clarify what you mean by just all altitudes?
So basically, in order for like the angles to be equal, it has to be a right angle, right? So just the intersection of all the right angles, or of all the altitudes, it's just the orthocenter.
Can you clarify what you mean by just all altitudes? Sorry, I didn't really get it.
So it has to be on the altitude from A to BC and the altitude from B to AC and the other altitude. So it must be the intersection, which is the orthocenter.
And the reason being? For that has to lay on the A altitude?
Because then the angles won't be the same.
Yes, indeed. So first of all, we can use a concept of phantom point. That if you let P, let's say, to be the orthogonal conjugate of O, then AP by definition should be orthogonal to AO, and similarly BP is orthogonal to BO. However, we previously had proven that the orthogonal Symmedian of AO is in fact AH, and therefore late H is in fact the orthogonal conjugate of O, kind of like a corollary from the previous result. Does that make sense? It is the unique answer. That's a great question. I believe you have a proof for it later. Why don't you think about it? Do you think it's gonna have a unique orthogonal conjugate? Yeah, since it's an intersection of three lines. However, think about it. Like three lines is not necessarily concurrent at a point, right? Like if you just have three random lines, they're not necessarily concurrent. So how do you prove if it is correct that they're gonna like be concurrent? So Vincent said that if there's only two Symmedians intersecting, there it is not an orthogonal conjugate. What do you mean by that? Okay, so how now let's try to prove that for oh yeah, so if you read under the first diagram on this page, that the proof for the concurrency of the three diagonal Symmedians is indeed going to be concurrent. Franklin, didn't I talk about the proof for this?
There's several ways of solving this. But like if you know what, I'll give a really easy proof if you know one of the theorems called Seva's theorem sign form. And basically what it says is that three Sevians are concurrent only if the sine of angle BAP over sine of CAP multiplied by the sine of angle ACP over the sine of angle BCP multiplied by the sine of angle CBP over the sine of angle ABP. Only if this quantity is equal to 1, then the Sevians are concurrent, but otherwise they aren't. But there's different ways to do this, and Stephen has outlined a proof underneath for you if you still don't know this, which is totally fine. In interest of time, I'll have Stephen explain the next section.
Okay, so let's briefly cover this it's like two pretty important racial lemma that mainly appeared in AIME and AMC calculation style problems. Those are still pretty useful in the Olympiad Games. So for example, the first one is stating that if you have two orthogonal lines, call them AP and AQ, and if you drop a perpendicular from D to the side AB and AC, and call them like PD and PE, and similarly, if you draw the projection of Q on AB and AC, and call them F and G respectively, and if dP equals to X, PE equals to Y, and what did I say? QG equals to S and FQ equals to R, you're going to have a really nice ratio out of nowhere that X over Y is equals to S over R. This is indeed a pretty nice lemma because it's pretty general that oftentimes you're gonna have two Symmedians in a triangle being concurrent. It's a really common phenomenon. And in addition, P and Q are just random points on the line, on the orthogonal line. So it is a really universal style result that could be used. So in order to prove it, we can use the idea of similar triangles because we're trying to prove a ratio being equal. So that we aim to show that triangle PDE is similar to triangle QGF, and assume that you have the knowledge of cyclic quadrilaterals. It's easy to prove that ADPE and AFQG are indeed cyclic. And through trivial angle tracing, which you can carry out by yourself, I think you have the capability to do that. And then you're gonna indeed prove that the two triangles are similar from the two angles being congruent. Is there any question on this lemma? Are we good? Okay, great. So for the next lemma, Franklin, can you scroll down, please? So this one is called the Steiner's ratio lemma. So this one states that for triangle ABC, if you have AD and AE being orthogonal, then you're also gonna have a really cool result. So this one states that BD times CD, BD over CD times B over EC is indeed equals to AB over BC squared. And this is going to be really important when we are introducing Symmedian here, so please pay attention in this result. And to prove it, we can motivate it by the BD over CD condition that BD over CD equals to the area of triangle ABD over the area of triangle ACD. And by the way, in here, the square brackets means the area of. So assume that you know like the trig representation of area. Assume you're good with that. And then we can write the area of triangle ABD as in AB times AD times sine of angle BAD. And then if you write it out for B times CE, and if you multiply them, and the left side of the result is going to be equivalent to the left side of the result you're trying to prove. And the right side, it's going to simplify directly to AB times BC. If you use some like algebra stuff. So now you prove this two really powerful results that I hope you're going to memorize for lots of computational style problems. Then you can recognize the orthogonal configuration.
Next, we will be actually defining the Symmedian. And it like sounds really simple, but and it sounds like really arbitrary, but it can turn up in a lot of places where you don't expect, which we'll get into later. So the first thing is the Symmedian is the isogonal Sevian to the median, which is basically saying that if AM is the median, then and D is the point such that angle BAD is equal to angle CAM, then AD is the Symmedian. And there's a lot of equivalent definitions. So let's start out with it. So the most simple equivalent definition, at least in my opinion, is reflecting the median over the altitude. I mean, reflecting it over the angle bisector. Can anyone tell me why that reflecting the median over the angle bisector will result in the symmedian?
So to start off, think about how do you like, what does it mean by reflecting a line over another line? Okay, so Kevin claimed that because angle MAE, well, what is point E here?
EA is the angle bisector.
Okay. So angle MAE is equal to angle EAD. That is indeed correct. So it is in fact not that deep. So if you just reflect it over the angle bisector, we're gonna have let's use the point E for that. We're gonna have by definition that BAE is equal to CAE. And because you're reflecting it over, DAE is also equal to MAE. And if you just subtract it, you're gonna get that BAD is equal to MAC, which by definition results the Symmedian AD.
Okay. Next, I'll go over another one. So this one actually has a typo. It should be BX over CX. But basically what we're stating is that if we have a triangle ABC such that BX over CX is equal to AB squared over AC squared, then AX will be the Symmedian. So I'll just go over the proof right now. Basically, it's because we can use the ratio lemma which basically, if you remember, states that bx over xc multiplied by the isogonal Symmedian, which we know is the median in this case, which is bm over mc, is equal to ab squared over ac squared. And this immediately gives us the result, since we know that the median is like bisects the side. So we know this is just equal to 1. So we get that bx over xc is equal to ab squared over ac squared, which is equal to c squared over b squared. Does that make sense?
All right, awesome. So now let's cover the second equivalent definition. Can we use the angle-Besseter theorem? Can you elaborate on how do you plan to implement the angle-Besseter theorem? Hello, Kel. Kel, would you please turn on your mic and it's all good. So now let's see the second definition, that if you have a point x on the I'm thinking about how to make sense of this. So the incentive for this definition is from the first racial lemma that states if you have two isogonal Symmedians, then you have the little racial lemma. So this is trying to go backwards, because that if you have the one from the median, it's like kind of inverse proportional. And if you have the because in the racial lemma, the ratio is kind of like flipped. So in this case, if you have a line or maybe just a point inside triangle ABC, such that the projection from X to AC and AB is equals to B over C, and that's going to equal to the kind of like the inverse of the ratio on the A median point, and therefore it's going to be the A Symmedian. I'm trying to explain it backward to make sense of it by the projection ratio lemma that we had proved before. Does that make sense? Good? Okay, great.
The next equivalent definition is going to occur in probably most of our practice problems, and also occurred in an AIME problem like 1 year ago. So you might want to pay attention for this one specifically. So basically, we have the tangents. So we have triangle ABC, let's draw a circumcircle. And then the tangents to circumcircle at B and C, let's let these meet at T. And AT will actually be the asymedian of triangle ABC. And how we prove this is we use areas using sign form. It's a very powerful tool. So it's a very good technique if you want to use it. When we look at the areas of ABT and ACT, and we have a bit of a solution sketch over here, but you can look over at in your own time.
Okay, so the fourth definition here is, I'd say, is shown second most frequently in the especially Olympic contests, with the most frequently one being the third definition that Franklin just mentioned. But this one is relatively advanced, so it states that for triangle ABC, if D and E are on side AB and AC, if somehow BDEC happen to be cyclic, meaning that they lay on the same circle, and then if you consider the midpoint of DE, and if you call that point to be F, and we claim that F is going to lay on the asymedian, meaning that AF indeed forms the asymedian. It's a really kind of surprising result on the first glance, but it's going to make more sense when we hit the, I believe, 2.5 section, the anti-parallel section. And this one is extremely useful during the contests. Wait, Franklin, can you scroll down a bit, please?
Oh yeah. Wait.
Wait, we just proved these, right?
Yeah.
Sure. Okay, so these are basically just the original lemma we talked about before, but then we are applying them specifically to Symmedians. So previously we had two orthogonal Symmedians, AK and AP, such that like they're just being random Symmedians that happen to be orthogonal. And now we're going to tackle specifically to the A-median and A-Symmedians. So the first one is called to be the Symmedian ratio lemma. And if P is on BC and it is on the A-Symmedian as well, then we can have the ratio to be BP over PC equals to C squared over B squared. And this proof is directly from the first definition of Symmedian if you happen to remember it. Franklin, you can scroll up a little. So, and if you read the proof for this one, it's essentially the standard ratio lemma that is covered in the length ratio section, I believe section 1.3. And the second lemma, let's name it to be the projection lemma for Symmedians. That if let's say A prime is the A median, and P is on the A Symmedian, and the projection of P onto A, B, and BC, we have X over Y. You can see the diagram because they C over B, where C is the length of AB and B is the length of AC. And the proof of this is directly from the second definition of the Symmedian. Franklin, you can scroll up a bit, please. So this one is essentially from the projection ratio lemma. So we can think for these two results as being direct consequences or specific cases for the two previous length lemmas. Franklin, then explain the section.
Okay, wait, I'm pretty sure wait, you were supposed to do this one, right?
Sure. So let's say that we have our dear friend A Symmedian again. And this time we're going to bring out the circumcircle of triangle ABC. So now we're going to see how Symmedian is going to interact with the circumcircle of triangle ABC, which is a really common suspect among the problems. So if you recall the third definition from the Symmedian in the section 2.1, so if you draw the tangents to the circumcircle, in this case the triangle ABB, we have them to meet at point T, that we know that AT is the Symmedian. And if you have the Symmedian AT to intersect the circumcircle, again at point C, and we know that, in fact, quadrilateral ABCD are harmonic. Can we get a quick show of hands, or how many of you actually are familiar with the concept of harmonic quadrilaterals, if any? No? Okay, great. Today's gonna be the first day you're gonna learn it. So if something is a harmonic quadrilateral, that means the product, so first of all, it is cyclic. And on top of that, it is cyclic. The product of the opposite sides are essentially equal. And we're saying that if you draw the point where the AC median is hitting the circumcircle, we're gonna have the 4 points to surround the triangle and the intersection point. They're gonna form a harmonic quadrilateral. And it's going to give you a really handy Lancer dot that's going to be used really often when you're tackling AIME calculation style problems, or even some other computational style problems, for example, HMMT and PUMAC. And by the way, this configuration shows up very often in those college bound computational problems. And the proof for this is rather a bit complicated. You can either length bash it or trig bash it. The synthetic proof would be really cool, but would be rather it'd be kind of crafty. So you can kind of consider to draw a line through T and intersecting AD and AB such that, okay, how do I annotate? Yo, Franklin, how do I annotate?
There should be a bottom in the bottom left corner.
Wait, where do you just draw it for me? Like a line through T that intersects AB and AD at a point, such that like AT is kind of like the antiparallel for BD. Like draws the antiparallel of BD with respect to T, please.
Could you elaborate again, please?
Oh, with respect to triangle ABD, draw the line through T that is antiparallel to BD. This is indeed a quite crafty construction. Okay, so having this line just means that if you see the bigger red triangle, this bigger red triangle is going to be similar to triangle ABD, which is going to give you this angle condition, further indicating that if you have the BDPQ quadrilateral, this quadrilateral is going to be cyclic, meaning the four vertices are going to land on the same circle. And you can use this construction to prove the result synthetically. Great. Is there any questions up until this moment? All right, great. This is a really specific result for harmonic quadrilateral. I'll save it for your own sake for further reading. And then here's a rather complicated fun fact that's related to Dumpty point and harmonic quadrilateral. I think for time's sake, we can skip this one for now.
Okay, so now we'll be discussing antiparallels and how they relate to Symmedians. So remember when we mentioned the quote unquote second most used way of like expressing a Symmedian, and that involved like antiparallels. So to refresh your memory, basically an antiparallel to a triangle ABC is basically a segment that passes through the, like in this case, AB and AC. Let's just call these points G and F, such that BGFC would be a cyclic quadrilateral. So all of these lines, if you do some angle tracing, you'll find that this angle will always be constant with respect to angles A, B, and C. So this angle, so which means all of these will have, so all such antiparallels will be parallel to each other.
Okay.
We have another definition. Let's just look at this diagram here. And basically it states that DE, this segment, is only antiparallel to BC if it's perpendicular to AO. And over here, we can just do like a lot of angle chasing to find that out. Actually, it's not that bad, but it's still some angle chasing. And I'll leave it to you, leave it for you to prove later on. Next, we have one more theorem. And basically, this one's where it actually gets important, and I think we referred to it in part of our equivalent definitions. But basically, if AD is the Symmedian and DE is anti-parallel to BC, if AD is the asymmedian, I should be more specific, then AD will bisect DE. And we can prove it by using one of the lemmas that I stated earlier. But I'll leave that for you to do because that's a really interesting proof, and it's also good for you to learn how to prove it rather than just me telling you all this stuff.
Okay, so can I ask the question on what is antiparallel again? So there's a few ways to introduce it. That one way you can say that is if DE is antiparallel with respect to line BC, it means that the quadrilateral BCDE, or in this case, FG is antiparallel to BC, that BC FG are cyclic. That's one way of introducing it. Or you could also say that triangle AGF is similar to triangle ACB in an inversive fashion, such that the reason it's called antiparallel is because if you draw the antiparallel of BC, call that GF. And the interesting thing is that if you draw the antiparallel with respect to GF, you call that to be DE. And then you're gonna find that DE is gonna be the parallel to AC. The proof is quite straightforward. It's just that if you take the antiparallel of the antiparallel, if you take it 2 times, it's gonna be parallel. And it's a really common configuration that occurs in geometry. Okay, so now we're going to introduce the Symmedian points that we have so first of all, for your trunk ABC, you have 3 vertices. And for each vertex, you're gonna have a Symmedian line, right? And a unique Symmedian line. And now we claim that for these 3 Symmedian lines, they're gonna be concurrent, meaning that they're all going to pass through a single point. And we are going to call this point to be the Symmedian point. And in some cases, it's called the Lemoine point because Lemoine, this guy, single-handedly offered almost all of the Symmedian point and beyond stuff. So the credit goes to him for this. And there are 2 ideas to prove that they're in fact cyclic. They're in fact concurrent. So first, we can apply the Silva's trig theorem because the 3 medians of a triangle are concurrent. And we can just trick it as how we prove the 3 orthogonal Symmedians are concurrent. And then we're gonna another idea to spin about this is we can use the length Siva, which is the normal Siva, and to combine that with the Symmedian ratio lemma. And you're gonna have a bunch of stuff are cyclic, like symmetric, and they're all gonna cancel out, and you're gonna have the 1 at the end. And the practice section for this is to find the orthogonal conjugate of the Symmedian point. It's quite straightforward. I'll just give it to you that it is in fact the centroid. And the reason is quite straightforward is because Symmedian lines are orthogonal to the medians. Franklin, do you want to start on this section?
Okay. So basically, sometimes you'll see this in computational contests. I personally haven't used this that much, but it could be useful for AIME if MAA decides to troll. But anyways, you can actually bash using this medium point, and it lets you, and you can find a ton of lengths involving this medium point. As you can see from these expressions, they're not pretty, and I don't recommend you memorize these because there's
That's true.
you drop something. So if you really need to bash, I'd recommend starting it from the top and just knowing the process, because that way you'll be able to prove it, not prove it, but like go on the spot. And I think it's a lot better than memorizing something like this, which is really easy to forget.
All right, so let me go into detail of the bash, which is not really pleasant for the geo people. So here's another typo, that BD over CD square equals to C square over B square. It should be BD over CD equal to C square over B square. So first of all, we have from our Symmedian ratio that BD over CD is in fact equal to C square over B square. So now our full picture here is that assume we know all the three lengths of triangle ABC, and if you construct the midpoint, and where the A median hits BC, call that point D, and if you introduce the median point K and the point E, such that point E is where the A median point hits the circumcircle of ABC. So, and our goal for this project is try to bash out every single length in this diagram. So here, let's first try to bash out BD and CD. This is going to be the easiest bash from here, such that we first know the ratio of BD over CD in terms of B and C. And in addition, we know BD plus CD because that is in fact just BC, which is A. And we know the three lengths of the triangles, we know that. So therefore, we can solve for BD and CD in terms of AB and C, and which is BD equals to A times C squared over B squared plus C squared. And also we have CD equal to B times C squared over B squared plus C squared. Does that make sense so far? Because I promise you, it's only gonna get more complicated rather than simple. All right, great. So now from the Symmedian point properties, they're geometric ones, that if you have triangle ABM, that triangle is going to be similar to AEC. And this result is going to be very useful to try to bash out the length of AE. Does that make sense of why they're similar? Would anyone give a proof of why triangle ABM is similar to triangle ACE? Okay, so Eden claimed we can use the square angle theorem such that ABC is equal to AEC because of the circle. And more importantly, if we have the Symmedian definition, we know that triangle angle BAM equal to angle CAE. And now we can use AA, and the two triangles are in fact similar. And now they're similar, we can use the similarity ratios. We can have A over AD equal to BC over BD. And observe here, like BD is a typo. A over, oops, the typo here is messed up. To correct, it should be AE over AM equal to AC over AB. Franklin, would you please correct that? Apologize, guys. My bad.
What exactly again?
So AE over AM is equal to AC. Bruh, I messed up. A over AB equal to AC over AM. Alright guys, you saw that. That's a really bad example for in the computational exams, Because if you mess up one single thing, all your bash is gonna disappear and you're not gonna get a point for the problem you work on for 20 minutes. So do not be like me, you guys. So anyway, if you have this ratio, you can represent AE in terms of AM, AC, and AB. And APAC, they're quite straightforward to calculate they're just given. And to calculate AM, would anyone propose a method to compute the A median of triangle ABC in terms of the length A, B, and C? Stewards is definitely a way. It is again not very pleasant. So there is a relatively more convenient formula. So Frank, let me dictate you. It's like b squared plus yeah, I think you memorized the formula in this way.
Wait, my bad. Okay.
Yeah, I think there's a coefficient of 1/2 or something.
Yeah, I have to multiply by 2.
Okay, that seems close enough, I think. Wait, maybe there's a factor of 1/2 on the outside. Yeah. Okay, great. So with this relatively more convenient formula, you can bash out AM, which is kind of unpleasant, and then we can bash out AE. Like, hear me out, this is not very cool and not very pleasant, but eventually in AIME you have to bash this. And in whatever competition you're gonna have to bash it. Until you go to the proof geometry, which is cooler. And now to recap, we have bashed out AD and CD, again with AM and AE. So now we're left with how to how to bash out AK and KE. So before we can bash out KD, we can first, what else are we gonna do with the 3 hours? Real. Oh yeah, and one suggestion is after you bash, especially in AIME, please double triple check your work. Or you're gonna silly the geometry problem like me. That's gonna be catastrophic. And you're going to miss JMO by like 1 point or 0.5 points. Like me. Or like Franklin. Anyway, so now to bash out AD, you can use the perfect point at point D. Are you guys aware of what is perfect point theorem? Yes? Okay, great. So we can do the perfect point at D, and we can know that BD times CD is equal to AD times DE. So BD times CD, we have previously bashed it out in terms of length A, B, and C. And for AE, we have bashed it out. And we can AD times DE is essentially the AE minus AD times AD. So now we have a quadratic in terms of AD and a bunch of whatever lengths. And it's quite ridiculous to solve it. But if you have to, you can solve it, So you can bash it. And at the end, you got that AD equal to 2BC times root whatever over B squared plus C squared. And this is honestly ridiculous to memorize. So you can, on the test, I hope they're gonna put relatively nicer numbers. So in this case, you can just remember to apply perfect point at D and just solve the quadratic. So now we have bashed out BDCD, AM, and BM and CM are trivial. And we had also bashed AD and AE. And we can calculate DE quite trivially. So the only final boss left to tackle is AK. And to tackle AK, we have to use area again. So we can see that the area of triangle BCK to BKCA, the quadrilateral BKCA, the area relation is going to be KD over AK. Franklin, do you wanna shade the areas?
Yeah, which ones again?
BKC over ABKC. So guys, is it obvious that the area of BCK over ABKC is in fact equal to KD over AD? Or more conveniently, the area of triangle BKC and ABC, the ratio of those is equal to the ratio of KD over AD. Is that good? Okay, or to elaborate on this? Yeah, as
Exactly.
I mentioned, it is the same base, and it's basically the height that matters, because the two triangles share the same base. Okay, and we have to find what is the area relation to those? Which is a pretty tough question, and here we cheated by using a more advanced result. So this result, I thought about putting it here, but I thought it might be too much for you guys. You guys can read on this. It's saying that if you have this median point K, if you're dropping the altitudes from K to A, B, A, C, and B, C, Franklin can draw the altitudes from K to B, C, and call it to be, I don't know, a KA.
KA.
Mm-hmm. Like the projection, yeah. And then similarly, if you construct the KB and KC, so in this case, you're going to have a really interesting length relation that the ratio of KA to KC to KB is in fact equals to A squared times C squared times A squared over C squared over B squared. So by using this lemma, you can have that the ratio of Ka over the rest is going to be A squared over A squared plus B squared plus C squared. And that's why on the denominator it is A squared plus B squared plus C squared. So AK over AD is in fact whatever A squared over B A squared over A squared plus B squared plus C squared. It's like a tongue twister. So you're gonna have this humongous expression that no one's gonna dare to memorize. But the more important thing, as Frank said, is going to be memorize the process of deriving this. So to recap on this crazy bash, that first we're gonna use the Symmedian point ratio lemma to find out BD and CD. And we're going to use the median formula to find out AM. And then we're gonna use a pair of similar triangles to bash out AE. And at this moment, it's gonna look pretty bad. We're gonna have to carry it out. And then we're going to use the perfect point at point D. And then we're going to use that to bash out AD. And then we are going to cheat. Use the more advanced result and bash out AK. But you really need to bash out AK. So maybe you can save that for the Olympia geometry. Is there any questions here? Please ask questions, because I know it's ridiculously ridiculous here. I'll wait for a bit for you to let us really dry knowledge to sink in. How do you find AK again? So in order to find AK, we want to first find it in terms of AD, which we had previously bashed out. So the ratio of AK over KD could be represented in terms of the areas. So I think we still have a bit of time left. Let me go in detail here. So let me type this in chat. I think it'll be better. So wait, Franklin, do you think you can write the stuff as I dictate you?
In chat. Okay.
Okay, so well, let me just say verbally, let's see. So the area of KD over AK equal to the area of triangle BKC. Franklin, then jot that down.
I'm writing in chat right now.
Okay. The area of BKC over the area of the quadrilateral ABKC. And you know that the area of the quadrilateral of BKBC is equal to the area of triangle ABK plus AKC. It's quite straightforward because you just cut the quadrilateral in half. And then you have the ratio of the stuff to be first the height from K to BC and K to AB and K to AC times the base. You know, the area of the triangle is like base times height, you know. And you know the base and the height could be found in terms of the ratios. And after you have the areas, if you really need to, you can bash out the area of the ratio of the areas. And after you find the ratio of the area, you can use AK over AD to find AK, which is a quite sad process to bash, but it could be our last resort if you really have to bash in terms of the Symmedian point. Okay, great. Is there any other question on this? Okay, keep in mind you can always reach out to us or just review the handout. Franklin, do you want to talk about the example problem 1?
Okay, so we have average MAA problem, which is obviously a bash. But anyways, this is from 2024 AIME 1. I wasn't lying when I said this was 1 year ago. But anyways, the problem states we have triangle ABC inscribed in this circle omega. And we have the tangents to B and C. And you should immediately think, and you see them intersect at D, and you see AD. You should immediately think about like Symmedians, since we literally like just talked about them. But hopefully you see this if you've memorized it. And then you'll see that AD intersect omega at another point, P. And then it gives you a few lengths of triangle ABC. And it wants you to find AP. And good thing we just covered some median point bashing, because you can go through the first few steps of it to find AP.
Okay, so let me pick it up from there. So now very unfortunately you encounter an AIME problem that involves the median, and even worse, it involves bashing. So they have the 3 side lengths of their triangle ABC. And now essentially you wanna bash out the Symmedian chord, meaning where the Symmedian intersects the circumcircle of ABC. You wanna find the length of AP. Yeah. So is there any brave volunteers who can tell us what is your grand plan for this bash? Feel free to open your mic and just say it. Keep in mind that it's a really recent AIME problems. DeepSeek. Alright, buddy. It's like literally last year. It's the last year AIME problem. And it's number 10. So it's very relevant to you if you wanna score a decent double digit on AIME. And it's like a quite recent years, it is very relevant for you. So feel free to work on this. Find the median length. Great. That's a great first step, using either Stewart or the median formula. And then similar triangles. Okay, great. Okay, since we still have some time left, do you guys wanna do you guys want to do the calculation yourself to see if you can actually get the right answer or not? Because very sadly in AIME, all you have to do is computations. Like, all that matters is that if you get the answer correct or not. It's not if you're on the right track or not. So let's try to get the computation correct. If you get the answer, try type a direct message to me or Franklin to tell us what you get. Okay, please work on this. You can use the length bash to help you if you need. Okay, once again, Franklin laid out the outline of the bash. Find AM and then use similar triangles. So, hey, think about it. If you get this problem right, you're basically nailing the reason you're AIME number 10, the double-digit AIME problem, within like 5 minutes or 10 minutes. You're gonna get a free point. $113. Okay, we have Winston having an answer. Okay, everyone, please keep working on this. Alright, I've received 2 correct answers so far. Good job. You
Yeah,
got it correct. Mm-hmm.
by the way, Evan Chen does have a section on Symmedians, but it doesn't go into that much detail. But if you want some example problems, there are some extras in there, I believe.
Wait, what chapter is it? From EGMO?
Chapter 4, section 6.
Wait, isn't chapter 4 like the analytical bash or no?
Chapter 4 is configs.
Oh, yeah. Okay, one more person have bashed this problem out. It's great if you think about it, like after 1 hour of learning, you cannot theorem nuke this AIME problem and you can nail it down within like a matter of minutes. You can get a lot of time later on in the exam for other problems.
Yeah, for that one really annoying P15.
Real, bro. Okay, I'm going to wait for one more response before we move on. Okay, that's very relatable. You get an imaginary number while bashing. I think about it, at least you didn't get a negative length for the side. It's not too bad. Could be worse. Okay. Yeah, Franklin, did you get any responses?
Not yet.
Okay. Hello, Aiden. Hi, Aiden. Can you open your mic and say hi?
Hi.
The answer for this problem is in fact 113. The length is 100/13. Then I present your solution, and Franklin and I can help you to like debug.
Okay, so I'll annotate. Okay.
Franklin, then I give him the annotation access.
No, I can annotate.
Everyone has access, I think.
Yeah.
Okay, so it's my screen.
So I'm pretty sure the median formula is so then you get that AM equals 13/2.
I believe that is indeed correct.
So and then the ratio of AM over CM, that's gonna be 13/4. No, 13/9.
Mm-hmm.
And then so you need to multiply 9/3 by 5. Oh, looking for AP. Oh my
Indeed.
god, I'm on DP.
Yeah, I think that's like okay. So do you wanna try to resolve this?
Okay. Then AM over AC equals 13 over 20, and then you multiply 20 over 3 or 13 by 5, so you get 100 over 13.
Okay, great. And do not forget that like in the final answer you're going to put like 113. Do not be the dumb kid that's gonna like somehow I don't even know how to put like 100 over 13. And shamefully, I did that like 2 days ago at a math competition where sadly, and I got that problem wrong because I didn't put the answer in the form I requested. So that's a kind of example of what you should do. You should, after you solve the problem, reread the problem to see like if you actually interpret it correctly, and that you have the answer in the format that it actually wants. So do not silly any geo. It's like painful, and you're going to crash out if you do.
Oh yeah, and read the answer extract carefully. Like I know this year's AIME one had like a 2025 minus like difference of like the answer in 2025, which is like really weird, but I think it's easy to like just forget those and assume it's like N mod 1000 and stuff.
Real. So we have the solution here in case you didn't solve it and you can refer it back to it later. And now let's see another problem. This one is a bit tougher. Actually, also is much tougher. So you can try this on your own later, but I'm gonna give you a head start to this problem. And I will lay out the solution steps too, so you can implement them later. So if you have ABC to be a acute scaling triangle with circumcircle omega, which is a really common layout in Olympia or even just computational geometry. So if you draw the tangent to omega at B and C, and if they intersect at T, so you should immediately be on alert when this configuration occurs because T is going to lay on the A Symmedian. And if X and Y are the projections of T onto AB and AC respectively, suppose that BT equals to CT equals to 16, and you're given that BC equal to 22. And now you're given a ridiculous condition that tx squared plus ty squared plus xy squared is going to be somehow equal to this weird number. And the question wants you to find xy squared, which is crazy. So the idea to solve this quite not very funny problem is you can find M to be the midpoint of BC as labeled in the diagram. Oh, and by the way, in the real problem, you're not going to be given these gorgeous diagrams drawn by GeoGebra or asymptotes. You're going to have to construct them by hand. So it's better to really know how to do geometry construction by hand. So in this case, you're going to like somehow construct all this mess, which honestly shouldn't be that bad. And if you call M to be the midpoint of BC, and then by angle tracing, you can have XYT, angle XYT is equal to angle XAT. That's because like AX, TY are cyclic, which is equal to MAC. And then similarly, TXY is equal to MAB. Okay, so let me repeat. Angle TYX equal to angle XAT equal to angle MAC. And similarly, you're going to have the other pair of the angle condition. And after that, it's gonna be the algebra work. You just finish the cool geometry part. And now you're gonna do a lot of science. triangle MAC and triangle XYT. And they're gonna get an expression. Scroll down a little, please, Franklin, to the solution. That 16 times sine A over 11 is equal to xy over AM. And then we can bash out AM by the whatever ridiculous expression that's given. So xy over AM squared is equal to 165 over 121. And then we are gonna use dual word, and we're gonna very unfortunately bash it again. And we're gonna do a lot of cosine bashing, and we are going to somehow find out the answer, which is sad. Okay, so here's the outline of the solution to this problem. Is there any questions for this? I kind of skipped the last part. It's very computation heavy. I really wish that tonight or tomorrow may have time. You're really going to carry out all these computation by yourself. It's going to give you a huge boost in the competitions that you're going to take later. Okay, is there any question on this? Or are you too confused to ask any questions? That'd be really sad. Okay, okay. And by the way, shout out to Vincent and then let me check. Charlie and Kevin for getting the example problem 1 correct.
And
I
also
believe
Steph.
you guys are going to go to that AIME and solve whatever 15 problems. And go to JMO and MOP. See you in MOP next year. Okay, is there any questions for this? Or maybe just Symmedians in general? Failed AIME? Okay, all good, all good. Bro, I failed AIME too.
I also failed
And,
AIME.
bruh,
I
very
still have
sad.
3
I missed
problems.
JMO by 3.5. It's pretty sad.
Don't miss JMO by 1 point. Like, don't be me.
Yeah, real. Vice words. Anyway, guys, the first year I took AIME, I kind of sold. I got like 6. And then you're gonna do better, you know. If it is your first year qualifying for AIME, like you shouldn't have like. Bro, what is Creddy saying? Whatever. Like, you know, it's like, bruh. Wait, Creddy. Have I seen the Think Academy class, bro? Okay, anyway, is there any questions regarding Symmedians? Or even in general? Okay, so before we end, let me lay out some interesting facts. So, speaking of geometry in general, there's something called cumulating cinders. Let me share the screen. Yo, Franklin, can you stop sharing, please?
Oh yeah.
The host disabled attendee screen sharing.
It's okay.
Or anyway, can you just share
It's
it?
okay. I'll make you host.
Cumulating cinder. So there's something called cumulative cinder, which is a collection of triangle cinders, which is really cool. You should Google that later today. It's basically like, you know, like the triangle cinders, like circumcinder, multicinder, and whatever. And the Symmedian point is in fact one of the cinders. So if you're going to keep pursue math competition, you're going to learn something called the barycentric coordinates. So you're going to have to memorize a bunch of bashing stuff. So I remember the barycentric coordinates for this median point is like ABC, I think. It's quite elegant, or maybe A square, B square, C square, I think.
It's a squared, b squared, c squared.
And if somehow I decide to keep pursuing geometry, you're going to learn about something called trilinear coordinates, which is not really especially applied in competition, but it's pretty elegant in terms of geometry. Remember, the trilinear coordinates is like it's also like a point a b c or something. It's like one of the barycentric coordinates is like ABC. The other one is like b square, b square, c square. It's like for future references. And that's the Kimberlin Cinder. There's the collection of around like 20,000 or so currently triangle cinders, and the Symmedian point is the sixth Kimberlin cinder. So for future references, that may or may not be useful one day when you become a barycentric person.
Oh yeah, berry bashing is not fun, by the way. Just saying.
Real. So you can either be a synthetic Jew, man, like you use geometry in geometry, like use actual geometry. Or also you could use bash, like I don't know. You can use the coordinates bash, or trick bash, or a complex bash, or a barycentric bash, or lots of bash. Or I personally prefer the just Symmedian for whatever. Like just I personally prefer synthetic methods. The you use geometry and geometry that makes sense, Like you just use similar triangles or cyclic quadrilaterals or stuff. Okay, so let's ask it again. Is there any more questions? Keep in mind you can ask other questions regarding homework in the office hour. Okay, so if there's no more questions, keep in mind to do the homework, and it's like the practice problems. Will homework answers be posted? Yes. Franklin and I took a long time and compiled a solution document. It's like it took us a lot of time, so if you have time, you can read it. Where do we submit the homework problems? Okay, so that's a great problem. That's a great question. You can either just send it to Franklin or me directly. I believe we have our email. And a lot of the problems are proofs, so please send them as image or PDF. And we can give you, it's fine if you do not submit it, but keep in mind if you submit it, and Franklin and I, who are really experienced geoman trust, and we can give you some feedback on how do you write your proofs, and how should your thinking process be for geometry problems. And please attend the office hour where Franklin and I will be discussing the solutions to homework problems. And there's a speaking of the homework, there's a really challenging problem. The last problem is quite challenging. I think Franklin, did you solve that?
Oh yeah.
EGMO?
Oh no. Oh no.
That took like really
The
long.
last
It was not
problem's
fun.
extremely challenging.
Yeah, it's from the European Girls Mathematical Olympiad. They say, I feel like it's manageable if you're like a geoman, but I think it should be a nice challenge for you guys. If you guys cannot solve it, you can just look at the solution and try to get the most out of it. Okay, so have a good night, guys. Goodbye.
Thank you.
I'm
Bye.
a fake Geo main. I'm actually a combo main.
Come on, man. Cat.
I'm dead.
Bye.
Goodbye.
Thank
Good
you for
night,
coming.
guys. Have
Wait,
fun
when I
with
stopped sharing,
geometry.
it cut the wait, when I gave you host, it cut the recording. So Wait, shoot, wait, can you stop the recording, Steven? I think you have the privilege now.